We're going to move on from this slide and talk a little bit more about the study of energy transformation, which is thermodynamics. Thermodynamics has two basic laws, the first and second. There are other concepts that are associated with thermodynamics, but these two basic laws are introductory and everybody talks about them. The first is that the energy of the universe is constant. So that idea gets expressed in many ways, but the idea is that energy cannot be created or destroyed. So it can be transferred and it can be transformed, but there is no creation of energy with regard to this concept of the study of thermodynamics. And the first law is also known as the principle of conservation of energy. And then the second law, well, actually, during the energy transfer, for some energy is unstable and lost as heat. So when energy is transferred, it's not transferred in an equal way. It's transferred and heat is lost. But that heat, again, if you added that into the whole process, the whole equation, you'd have the same amount of energy. We're going to talk about a concept called entropy, where that heat loss creates less order. And that's definitely true with regard to this transfer of energy. It's not lost, but it becomes more dispersed. And the second law is that energy can't be changed from one form to another without the loss of usable energy. And the key word there is usable energy. So this giving off of heat, what you have in this nice bear picture is the bear is eating a salmon. Must be salmon run season. The bear is very excited eating this salmon. Salmon is a preferred food of bears. And that then is going to be broken down by the bear's body, metabolically broken down, so that that bear can run after more salmon or run away from something, whichever the bear is doing. But in that kinetic energy, heat is going to be lost. So the energy, that chemical energy that came from that salmon, is going to turn into kinetic energy for the bear, but in turning into kinetic energy, there's going to be some loss in the form of heat. And then on the other side, you have chemical energy, the ice cream being turned into kinetic energy for the kids. You have light energy being turned into chemical energy by the plants. This concept of entropy, there's the word that I'm referring to, that there is always going to be this unavoidable conversion of energy into a form that is less organized or more dispersed. And I think I kind of like the word dispersed because when we think of less organized, it's not going to serve us when we look at plants, and in visually anyway, they look much more organized, but the energy is much more dispersed. But speaking of that, then I have an image where it's a visual. So low entropy, so high energy or high potential energy. So low entropy, so the low level of lack of dispersedness, which is not really a word, but it fits here, or high level of organization. That's the low entropy. So with low entropy, you have high level of organization or potential energy. And then high entropy, you have this randomness with regard to the particles. Still the same amount of particles, still the same amount of energy, but the energy is dispersed throughout a larger area. And then you have this concept of spontaneous processes. This just means that this process is likely to occur without energy input. Just like if you, I guess probably the one that I have here, the car explosion or rusting. And one of the reasons why I like those two examples, and I have a picture of rusting on the next one, is when you think about it, there really isn't, I mean, you really have to work hard to keep your car from rusting. I have a pretty old car, keep it in a garage, but if I didn't keep it in a garage, I probably would have to watch out for rust. I would have to clean the car regularly, maybe wax the car regularly. I would put much energy into keeping a rusting behavior from happening. Rust is a spontaneous process. It acts with very little energy input, but you can also, so you can have one that's very slow acting and spontaneous, or very quick acting and spontaneous. Now, an explosion needs input for that explosion to happen, but not very much, and the amount of energy that's released is huge. In terms of our universe, energy flows from an ecosystem in the form of high entropy and exits in the form of lower entropy. So I need to relook at my picture, it looks like there, in terms of entropy. Entropy is the measure of disorder or randomness. So energy flows from a system in the form of very random and exits in the form of lower, more order, I guess you might say. In my mind, it seems kind of backward, but if you say it over and over again, it only because, I guess, because we tend to enjoy order or like order, but think of high randomness with regard to entropy. Second law of thermodynamics, a little bit more, just so that you have this in your head, that just because we are creating more and more complex organisms, that second law of thermodynamics isn't violated, because entropy, defined as the dispersal of energy overall. So we seem to be making a more ordered or a more high concentration of energy in an individual form, but overall the universe's energy is dispersing. So we have to look at the big picture. And the image here, although it's kind of fun to see this, particularly this, to see kind of a summer type idea any time of the year, but you have a very organized dandelion that a great shape, but just a little bit of wind is going to disperse that organization all over the place. And then you have a bunch of dandelions. This concept of free energy, and one of the reasons why G comes in here is there was a professor at the end of the 1800s, so 1876 actually, and he was working, his name was Gibbs, and so that's why we get this word Gibbs free energy. He did a tremendous amount of research on the idea of free energy, and free energy is the change or the amount of is the portion of a system's energy that can perform work when at a specific temperature and pressure are uniform throughout the entire system, as in a living cell. So let me repeat that. That comes straight out of your book. Free energy is defined as the portion of a system's energy that can perform work when temperature and pressure are uniform throughout the system. So that which is, I guess you can think of it as similar to potential energy. So what's available to do work, but that has to be under certain controlled conditions, temperature and pressure. And what happens is the calculation of it is what Professor Gibbs did. And so free energy conceptually is a method that tells us whether a chemical process will take place spontaneously or non-spontaneously. otherwise known as if something is a negative delta G, and we get this delta G, delta, and then G is for Mr. Gibbs, a reaction will happen spontaneously. If it's a positive delta G, it's going to be a non-spontaneous reaction. And so the calculation is to determine whether a specific reaction will happen spontaneously or not. And it's a relationship between this term enthalpy, which is equivalent to the total energy of the system minus entropy. So the total energy minus entropy, which is the which again is the concept of randomness, is a measure of a molecular disorder or randomness. And we do tend to work toward randomness as a universe. So there are many spontaneous reactions taking place, but there are many reactions that are non-spontaneous. In our image, we have our monkey here sitting under a banana tree, sleeping, not putting forth any energy whatsoever. But the chance that if that monkey sits under that tree and sleeps every day, the chance that those bananas will fall on his head or fall so that he can eat them is very high. So the chance of a spontaneous reaction, meaning these bananas falling out of the tree, is high because that's what bananas do. They fill up, they get heavier, more full with water, riper, and they're eventually going to fall out of the tree. But unfortunately, the chance of this monkey learning everything there is to know about biology is not high. It's not high that's going to happen spontaneously, so the monkey has to put a lot of energy in. It's not a spontaneous process, a lot of energy in to trigger the process. So that's that concept of free energy. Basically, it's a way to calculate whether reaction is going to take place or not. And it isn't an all or nothing. If it's spontaneous, again, how much reaction, how much energy is going to have to be put in to create that quote on spontaneous reaction. With all due respect, even a can of gasoline, which will ignite, but you have to start it with a match, etc. Or whether how much energy needs to be put in if it's a non-spontaneous reaction. And then the little bit more illustration of this. The free energy, again, is the measure of a system's instability. So whether it's spontaneous or not, its tendency to change to a more stable state. So its instability and whether it wants to move to a more stable state. During this spontaneous change, free energy decreases and the stability of the system increases. Equilibrium is the state of maximum stability. The only systems that reach equilibrium are closed systems. And closed systems, when they reach a state of equilibrium, no more chemical reactions take place. So once equilibrium is reached, the system stops metabolic behavior, and that's basically our definition of death. So we are an open system. We never reach equilibrium. We are always working on moving energy one way or the other. And if it's spontaneous, it can perform work only when moving towards equilibrium. So a spontaneous system is going to move towards equilibrium and then die. And then that's this concept. We're going to talk a little bit about the image that we have here, but we are running out of time on this one. But what you have here is these terms, exergonic and endergonic. And an exergonic reaction is one that will release energy. Endergonic reaction is one that is going to absorb energy. And so we'll pick this up on the next one to talk about these terms more.